representing our director, Professor Antonio Carlos Hernandez. Unfortunately, he could not be here today. He had a meeting in São Paulo, so he asked me to represent him in this little ceremony. And the idea is to express our gratitude and happiness to have you here today, you both, Alan and Bill. You know, such great scientists, and they have made many contributions to physics. As you know, Bill is the 1997 Nobel Prize winner for cooling atoms with lasers. And Alan is he got last year, 2010, the Wolf Prize for his contributions. You know, the Einstein-Podolsky-Rosen, he was the first one to do the experiment that settled this paradox. And so, for us, it's a great pleasure. It's to have here such great scientists is an example for us to follow, especially for the students. Okay, and so the director asked me to give these plates. I'll read the plates. First one to Professor Alan Aspect in recognition of his pioneering and outstanding contribution to the progress of Brazilian science through collaboration with our institution. Okay. São Carlos, São Paulo, Brazil, June 3rd, 2011. So these are. Oops.
Well, thank you very much. I'm very surprised. I was not expecting to get that just this morning. Otherwise, I would have dressed less casually. But anyway, I'm very happy because I came here for the first time in 88, correct, Vanderlei? 1988, not 18, okay? And it has been a long series of exchanges with Vanderlei and his group. We meet everywhere in the world, including in Paris and in San Carlos, but in many other places. And I'm always impressed to see how much progress have been done here in this country.
And then to Professor Willian Phillips, in recognition of his pioneering and outstanding contribution to the progress of Brazilian science through collaboration with our institute. So, São Carlos, São Paulo, Brazil, June 3rd, 2011. Okay.
Well, thank you very much. It's always a pleasure to be here. In fact, officially, I'm a member of this institute, so coming here is really for me coming home, and we've had a very long relationship with this institute. I've even done experiments and published papers here at the institute, and we've always been very happy to welcome visitors to our laboratory from this institute, and we hope that these kinds of relationships in both directions will continue and will become stronger. Thank you very much.
Well, thank you all, and thank you to Vanderlei for organizing these colloquiums. I mean, now I ask Neto to do the introduction.
Good morning, everybody. Welcome to the colloquium, and today I have a very distinguished speaker, Professor Willian Phillips from NIST in Gettysburg. Just a brief summary of his career. In '76, he got his PhD from MIT, and from '76 to '78, he was the Weizmann postdoctoral fellow at MIT. And after that, in '78, he moved to NIST at the time called the National Bureau of Standards. And since '92, he's faculty of the physics department at Maryland University. That's a joint appointment. And Phillips is well known for his developments on cooling, laser cooling. And it's very important breakthroughs on laser cooling techniques, and I wish to give some words about that. In '87, he was the first one to show that with laser cooling, you can cool down atoms below what the theory at the time said it was possible. And this is related to what is called the Sisyphus effect, and it's a non-trivial effect that relates the polarization of the light and the quantum state of the atoms. And he was, for this development, it was possible to cool down atoms to very low temperature of order microkelvin. And further developments on that was possible to cool down even further, and possible to achieve Bose-Einstein condensation, that is Nobel Prize from 2001. But he won the Nobel Prize in '97 for this development on laser cooling. And his motivation at the time was about doing very good atomic clocks. And atomic clocks are changing our technology, are changing our society, because if you really have a very precise device to measure time, you can, for instance, build our GPS that we have nowadays. And other developments on laser cooling is that we can study Bose-Einstein condensation, as I already told you, and the behavior of atoms at very low temperature, and the quantum behavior of that of the matter. And even here, this open area of research in physics that is called now optical cold atoms in optical lattices, where we can study very fundamental and basic questions of physics, of condensed matter physics, like the multi-insulator superfluid phase transition. And also we can study turbulence, quantum turbulence, as Vanderlei is doing here in the department. So this, I would like you to appreciate how this he's pursuing on laser cooling open a new area of physics and open new possibilities for development of technology and science. Without further delay, Professor William Phillips.
Thank you. Well, as always, that sounds a little too loud. As always, it's a great pleasure to be in San Carlos. I think that the last time that I was here and talked to an audience this big, it was more of a circus performance. And there were explosions and levitating things. So if you came to this talk expecting to be entertained, then I think you made a mistake. I'm afraid this talk is going to be a lot more hardcore physics, but I hope that if you're not entertained, that at least you may find something interesting in some of the recent experiments we've been doing at NIST. So I'm going to be talking about synthetic electric and magnetic fields for ultra-cold atoms. And this is work that has been led by Ian Spielman and postdoc Rob Compton and graduate student Karina Jimenez Garcias, postdoc Yuju Lin and undergraduate Abigail Perry have been the people who have done most of the work that I'm going to be telling you about today. Trey Porto is also a senior member of the of the team. And recently, Lindsay LeBlanc and Ross Williams have joined as postdocs for the next generation of experiments. We're all at the Joint Quantum Institute, which is a joint institute of NIST and the University of Maryland. And we're supported by all of these agencies that have many letters in their names. But I just want to say a few words about the Joint Quantum Institute. A few years ago, NIST and the University of Maryland decided that we should join forces and create an institute to study coherent quantum phenomena. And we've been having a lot of fun studying quantum phenomena in both condensed matter systems and in atomic systems. And as you'll see, the work that I'm going to tell you about today is a kind of crossover between condensed matter systems and atomic systems. And we get a major support from the National Science Foundation through a Physics Frontier Center that we've established within the Joint Quantum Institute. So these are the people who have done most of the work. Ian Spielman is the inspiration and the leader of this work. Karina and Yushu and Rob have done the main part of the experimental work, and Trey Porto, along with myself, have contributed some ideas. There's another very important player, and that's rubidium. That's the atom that we use for laser cooling and Bose-Einstein condensation. So what is the whole idea about making synthetic fields for cold atoms? Well, we've been having, as you've heard in the introduction, a great deal of fun in the past decade and a half working with quantum degenerate gases. First with Bose-Einstein condensation, and these are the famous pictures from Eric Cornell's laboratory in Boulder, showing the evolution of a quantum gas as it goes toward quantum degeneracy. So in 1995, the first Bose-Einstein condensate was observed in Boulder, and not too long after that, Fermi gases were made quantum degenerate, and these developments of making quantum degenerate gases have opened up lots of new avenues of research. And one of the most interesting avenues of research has been the simulation of simple models that are used for condensed matter systems. It turns out that there are a lot of simple models that people use to describe condensed matter systems. But even though the models are simple, their solutions are not simple. And often one cannot get direct calculations of these relatively simple models to find out how the model behaves, and then to ask the question of whether the model in fact describes reality in these condensed matter systems. And so one of the goals of cold atom research has been to simulate these simple models and to see experimentally what the results are from the model. And a lot of interesting things have happened. The Mott insulator transition, the BCS-BEC crossover in Fermi gases, Bloch oscillations, Anderson localization. A number of important things have been done using cold atoms as a way of simulating, as a kind of a stand-in for the electrons in condensed matter systems. But there is a problem. And the problem is that these atoms are neutral and electrons are charged. And very often, not always, but very often, the charge is something that's very important. And the interaction of those charged particles with externally applied fields is an important feature. Now, it's not too hard to simulate the action of an electric field on electrically charged particles with neutral particles. We do it routinely. For example, if we want to observe something like Bloch oscillations, the idea of Bloch oscillations is you have a perfect lattice. It has free electrons in it. You apply an electric field. The electrons accelerate until they reach a velocity that allows them to Bragg reflect from the lattice. They reverse their velocity, and then they continue to accelerate. This is something that's very difficult to observe in a real condensed matter system, but it turns out it's relatively easy to observe in a cold atom system. And how do we do it? Well, one way is to put the atoms into a lattice, an optical lattice formed by the interference of two laser beams, and then simply move the lattice. In the moving frame of the lattice, if the lattice is accelerating, there is a force, an inertial force, which can be thought of as being like an electrical force. And so it's easy to simulate the action of an electric field. We could also use a gradient magnetic field on atoms that have a magnetic moment. This produces a force very similar to an electric force. So that's easy. But how are we going to simulate the effect of a magnetic field on a charged particle? One of the most wonderful things that happens with an electrically charged particle in a magnetic field is that when it moves, it experiences a Lorentz force, this V cross B force that produces things like cyclotron motion. How will we simulate that with a neutral atom system? Well, one way is to rotate the sample. So if we have a system and it's a trapped gas and the trap is slightly asymmetric and then we rotate it, if we go into the rotating frame, we know that there appear some inertial forces, the centrifugal force and the Coriolis force. And the Coriolis force has the right form because the Coriolis force has the form of V cross omega, where omega is the rotational vector. And that then means that we can think of the rotation as being an effective magnetic field. And this has produced all sorts of wonderful results for cold atoms. People have rotated traps and seen that vortices enter the Bose condensate, just as would be the case, for example, in a superconductor. When you apply a magnetic field, that vortices appear when the magnetic field is strong enough. But there is a problem. And the problem is, one of the many problems, I should say, is that with this centrifugal force, there's a limit to how fast you can rotate. You can't rotate any faster than the rotational frequency that will make the centrifugal force bigger than the confining force of the trap. And very often, your trap is asymmetric. In fact, it must be asymmetric in order to be rotated, and that means that one direction will become unstable before the other direction becomes unstable. And this makes it very difficult to work at a high enough effective magnetic field to do some interesting things, like get your system into the regime of the quantum Hall effect or the fractional quantum Hall effect, which are regimes of very intense current interest in condensed matter physics. And so we look around for a different approach to produce a synthetic magnetic field. And to give you an idea about how this different approach works, let's think for a moment about the Hamiltonian for a particle in or not in a magnetic field. If I have a free particle, its Hamiltonian is just p squared over 2m. And the energy of a particle as a function of its momentum is just this parabolic dispersion curve that is centered at momentum equals 0. Now, if I put on a magnetic vector potential, then we know that the Hamiltonian for a charged particle in a magnetic vector potential is the quantity P minus Q times the vector potential, QA, that quantity squared divided by 2 times the mass. In other words, we've simply replaced P with P minus QA. This is the usual replacement for the momentum if we want to write the Hamiltonian of a charged particle in a magnetic vector potential. So we can think of the effect of a magnetic vector potential as simply changing the origin of the dispersion curve of a particle. If we shift the minimum of the dispersion curve of a particle, we have done the equivalent thing to putting it into a magnetic vector potential. And if we can then figure out ways to make that magnetic vector potential have a curl, then we will have a magnetic field. If we can make that magnetic vector potential be time-dependent, we can make an electric field. So that's the core of the idea is to change the dispersion curve of the atoms so as to make it look like the Hamiltonian has a magnetic vector potential, and then make that magnetic vector potential spatially dependent or time dependent to simulate a magnetic field or an electric field. So how is it done? Well, it's done with optics, because that's what we know how to do. We know how to shine lasers on atoms and make them do interesting things. And in particular, it's done by a Raman coupling, where we have, for example, two ground states. These might be separated by a Zeeman splitting or a hyperfine splitting, and we couple them together with two laser beams. And I'll show you in a moment why this is capable of altering the dispersion curve. But a number of people have had some wonderful proposals along these lines. And a few years ago, Ian Spielman came up with a different approach, which is the one that I'm going to talk about. But I just want to mention that there are a number of other approaches that are being pursued in other laboratories with a great deal of vigor. So how can we change the dispersion curve? Well, let's imagine a very simple case where we think about an atom that has two slightly non-degenerate ground states separated by some frequency delta omega, and they're coupled together by two laser fields, a blue laser field coming from the left and a red laser field coming from the right. These two laser fields are different in frequency by approximately delta omega, and in this example, they're separated by exactly delta omega. So we are on what we call Raman resonance. We are resonant for going from this state to this state, and off resonant for this intermediate transition to the excited state. And for the moment, I'm going to assume that the laser beams are there to make that resonant transition, but they don't in fact do anything. In other words, there is no Raman coupling, there's no matrix element, but I'm just going to ask about what the energy of the system is when I count both the energy of the atom and the energy of the photons. This is a common way of thinking about a system that is an atomic system that's coupled to an optical field. It's the dressed atom picture that was invented by Claude Cohen-Tanucci. So the idea is that I want to think about the these two different states, and I want to think about their dispersion curves as a function of the momentum. And of course, each of the two states has a dispersion curve that is the usual free atom dispersion curve, the p squared over 2m. Now, I've drawn them offset by a certain amount of momentum here, and that momentum is the momentum of two photons, the momentum that would be transferred if an atom absorbs a photon, a blue photon, and is stimulated to emit a red photon in going from the plus state to the minus state. Then the atom will pick up the momentum of two photons. And I've separated these two curves by that amount of momentum, and you'll see why in a moment. Now, the energy of these, it's my watch telling me that it's 11 o'clock and time to take some medicine, but I'll just ignore that. It's one of the punishments for growing old is that you have to take medicine from time to time. And of course, the other punishment for growing old is that you have no memory, so you have to set your watch to remind you that you have to take the medicine. And then the other punishment for growing old is that you become ornery. So you just ignore all these things, and then... Okay, so what we have here is an atom in this state, and with a certain number of photons n in the red laser and a certain number of photons n in the blue laser. And over here is an atom in the minus state that has one less photon in the blue laser. In other words, it's absorbed a photon from the blue laser, and one more photon in the red laser because it's absorbed a photon from the red laser. And of course, those photons have different energies, but the state has a different energy as well. And because we're on Raman resonance, these two states have the same energy. But let's talk about the momentum. if I absorb let's say that I have a momentum, a negative momentum in the +1 state. In other words, the atom is moving to the left. And so let's say that I'm here at the place where these two curves are degenerate. I can absorb a photon from the left and emit a photon on the right, and I'm now in this curve, okay? And I'm moving to the right. And I'm choosing to label both this state and this state with the same quasi-momentum, because there is some momentum that is the same for both of the states. It's the momentum that this atom had before it exchanged the photons. So these two states belong to the same family, and that family is labeled by what I call the quasi-momentum K. So this point, and every point on this graph, has two possible states that correspond to the same quasi-momentum, and the real momentum, the mechanical momentum of the atom, is different in those two states by the momentum of two photons, because in order to go from one to the other, you have to absorb and emit those photons and change the momentum. Okay, so that's the picture. And so far, we've done nothing. All we've done is a different kind of bookkeeping about the energy and the momentum of these states. Now we're going to do something. We're going to turn on the coupling between the atoms and the light field. And in particular, turning on the coupling between the light fields and the atoms will turn on coupling between this state and this state. And in particular, this level crossing here will become an anti-crossing, because that's what always happens in quantum mechanics. When you have a level crossing and you have coupling between the two states, it becomes an anti-crossing, and that's what we're going to do. So now we've turned on the coupling, and this level crossing has become an anti-crossing. So we've separated two states, and of course the two states are not the original states. They're coherent superpositions of the two original states, and we call them dress states. And if the coupling is strong enough, then the lower dress state will look approximately like this dashed line, and the upper state will look like this dashed line. They will both look approximately like parabolas. They're not exactly parabolas anymore, but they're approximately like parabolas. And if we stay down here at the bottom, we can treat these dispersion curves as if they were parabolae, and think about them as being a new kind of particle with a different effective mass. But in this case, when I have 0 Raman detuning, the position of the minimum of the dispersion curve is unchanged. That means we have 0 vector potential. But if I change the detuning so that it's no longer on Raman resonance by making, see what I'm going to do is I'm going to make this red vector a little bit longer by making the frequency of the red laser a little bit higher. And that will make the energy of the atom that absorbs the red photon, that is the minus state, a little bit higher. And so we now have, if I don't have any coupling, I have these curves. And when I turn on the coupling, you see this bottom curve is shifted over, because as you can see, this average curve of these red parabolae is shifted to the right. So the minimum is shifted to the right. So this thing has a vector potential, a non-zero vector potential. And here's the real atomic system. I was showing you a sort of cartoon version. Here's the real thing. This is rubidium in the electronic ground state of F = 1. We turn on a magnetic field to lift the degeneracy among the different magnetic sublevels, so that we have 3 states instead of 2. But the physics is very similar with these 3 states. So here are the 3 states. We turn on lasers coming from opposite directions. Here's the cartoon of the experimental setup. We have a magnetic field in this direction that lifts the degeneracy. Now this is a real magnetic field, not the artificial magnetic field that we're trying to create. It's a real magnetic field whose only effect is to lift the degeneracy of these states. This magnetic field will not produce a Lorentz force. It cannot, because it doesn't have the right properties, because our atoms are neutral. But it lifts the degeneracy, and that's very important. So we create this Raman coupling, and here is an explicit calculation of what this Raman coupling does. So the thin black lines are the unperturbed curves when we have no Raman coupling. The red lines are what happens when we turn the Raman coupling on, but the detuning is 0. And then we get this lower curve, which has its minimum at 0. It's a much broader curve, so that means the effective mass is larger than the real mass of the atoms. But when we change the detuning, then the minimum of that lower curve shifts over, and the amount by which it shifts is proportional to the effective vector potential. Now, in fact, we probably shouldn't talk about the vector potential. We should talk instead about the product of the effective charge and the effective vector potential. Both of those things are fictional. Their product is this displacement of the curve, and that product has the units of momentum. And so the amount by which this is shifted in momentum is the amount by which Q times the effective vector potential has been applied. So here again is a picture of the experimental setup. We have a Bose condensate here. We have a real magnetic field in this direction. We have counter-propagating laser beams. And all of this is happening in the XY plane. And it is in the Z direction that we're going to produce our effective magnetic field. So when we turn on this coupling, we will get a synthetic magnetic vector potential. And if that synthetic magnetic vector potential has a gradient of the detuning, which is gotten by having a gradient of the physical B field, it will produce a synthetic B field, something that has the effect of having a Lorentz force, as we will see in a moment. And as it turns out, putting a simple linear gradient in this direction is equivalent to putting a curl onto the A field. On the other hand, if we were to put a time dependence onto this, then we would create a synthetic electric field in the plane in the opposite direction as the magnetic vector potential. Okay, so that's the idea. That's what we want to do. So now let's do the experiment. So here again is the picture of the energy levels. So the red curve is the dressed curve. And what we do is we turn on these Raman fields in a certain way, which is actually rather complicated, and I don't want to go into it, that puts the atoms here. Now, I'll just say why this is non-trivial. We create the atoms in the -1 state. And then when we turn on the Raman fields, if we didn't do anything, the atoms would be here. They would not be here. And that's not what we want. So we have to do something rather complicated where we turn on radio frequency fields and Raman fields adiabatically, and the trap itself plays a role. So I just want to tell you that I'm glossing over a lot of details that are essential for doing the experiment right, but I think we don't need to worry too much about them now. The point is we end up with a Bose condensate, and it is here, which is to say it's at rest in the laboratory, and it has no vector potential. Now, you might say, well, why are you saying it has no vector potential? We all know that vector potentials are gauge fields, and I can choose the gauge to be anything I want. That's absolutely correct. I'm going to choose the gauge such that when I have this curve, it's 0. and we're going to measure that vector potential. And people say, how can you measure a vector potential? How can you measure a gauge potential? Well, we measure it in a particular gauge. And the gauge we measure it in is one in which the vector potential is exactly equal to the displacement of that curve from 0 quasi-momentum. Okay, so we put the atoms here, and then we do our analysis of the state composition of those atoms, and the usual way in all of these experiments is you simply turn off all the fields. You turn off the trap, which I haven't really mentioned here. You turn off the magnetic field, you turn off the laser fields, and you allow the atoms to propagate freely. Now we do have an additional field. We have a gradient magnetic field so that the different magnetic sublevels separate as if in a Stern-Gerlach experiment. So the atoms move according to their mechanical momentum in one direction, and in the other direction, we separate them according to their magnetic sublevels. So in this direction, we have their mechanical momentum, and in this direction, we have their magnetic sublevel. Now, what is this thing going to look like? Well, remember where it came from. It came from the superposition of three curves, one of which had m equals 0, one of which had -1, and one of which had +1. The one at m equals 0 has a mechanical momentum of 0. The one at -1 has this mechanical momentum. So it has a mechanical, because remember, they all have the same quasi-momentum. So this one has a mechanical momentum that's a positive mechanical momentum, and this one has a mechanical momentum that is a negative mechanical momentum, because it's at the minimum that the mechanical momentum is 0. So what we're looking at is something that's going to be a superposition of 3 different spin states and 3 different momentum states, and that's exactly what we see. The main component is m equals 0, and that has momentum equals 0. A small component at m equals +1, and that has a negative momentum, you see, because +1 has a negative momentum at the same quasi-momentum. And -1, the m equals -1, has a momentum of +1 at the same momentum, because that's this curve, and this is on the right-hand side of the minimum, so it's got a positive momentum. So this is just what we expect, and it's by looking at pictures like this that we're going to tell what the vector potential is when we make it non-zero. Okay, so, well, here, that's just the same picture again. People say that physics is dry. Okay, so now what we're going to do is we're going to change the detuning of the lasers so that we will shift this curve to the right. So here are the new dressed pictures, and we do exactly the same thing. We change the detuning. We do this by changing the magnetic field. We change the detuning by changing the magnetic field, and we do it slowly enough that the atoms adiabatically follow and they end up here. And we do exactly the same thing. We turn off all the fields and let the atoms go away freely. They separate into M states in this way and into mechanical momentum states in this direction. And this state, the one that has M equals 0, has shifted from here. This is where it was before. It shifted over here. This tells us that it has a non-zero mechanical momentum. It tells us where the minimum of the dispersion curve is. That tells us what the vector potential is. All the other ones have also shifted over. And you also see that the distribution has changed. The number of atoms in each M state is different. We have fewer atoms in the m equals -1 state, more atoms in the m equals +1 state than we had before. Why is that? Well, look. You see, this curve, you just ask yourself, what is it made up of? It's made up of more of this than in the case where it was symmetric, okay? So we have more +1, and we have less -1, and we still have a lot of 0. So that's why we have more +1 and less -1, because the state composition has changed in this way. Now, another important thing to look at is that the total mechanical momentum of the atoms is still 0. Because when we do this in the laboratory, the atoms are not moving. We turn on this detuning, the atoms move over to this point. The quasi-momentum is non-zero, but the mechanical momentum of the dressed atom is 0. It's not moving. Okay, it's in a trap. It's not going anywhere. How can that be? Well, look at the distribution of momenta and the populations. We have a lot of population with a positive momentum. We have some population over here with a negative momentum, and we have a very tiny population with a larger positive momentum. When you add it all up, it adds up to 0. It's always the case for all of these pictures. If we add them up carefully, we always find out that the total momentum is 0 because the atoms are not moving. We've changed the detuning even more so that the minimum is here. And now we see that we've moved these positions even more. So this atom, the m equals 0, the one that tells us directly what the vector potential is, it's moved all the way over here, almost 2 units. Most of the population, on the other hand, is in +1 with almost no momentum, which is just what you expect. Remember, the atoms aren't moving. So most of the atoms are going to have to be in the state that's not moving, and that's now the +1 state. Just looking at it again, you see that the further we move this over, the more and more it's going to be like the +1 state, and it's going to be very close to not moving. It's moving a little bit in the negative direction, and all the other ones are moving in the positive direction. There's hardly any left in -1 because we're so far away from that. So everything is working just as it should. So now we plot the measured vector potential, which is also the measured shift of the minimum of the potential, the measured quasi-momentum, as a function of the detuning of the Raman lasers from Raman resonance, and we get this curve. Okay, and this just shows you that at the center, where the vector potential is 0, we have a symmetric curve like this, and at the extremes, where the vector potential is large, either positive or negative, we have a curve that's been shifted over in one direction or the other. And this was published a few years ago in Physical Review Letters. And you'll also notice that there is a limit to how much vector potential you can have. And that limit is twice the photon momentum, because that's as much momentum as is available in the system. You can't shift the minimum of the potential any further than 2 photon momenta. So that's the limit to how much vector potential can be applied. Okay, so now we're going to try to do what we came to do, which is to make a synthetic magnetic field. After all, a uniform vector potential is pretty boring, right? It doesn't do anything. So now we're going to make a non-uniform vector potential so that it does something. So the idea is we turn on this field that lifts the degeneracy of the magnetic sublevels. We put a gradient on that so that there will be a non-uniformity of the vector potential. For these experiments, we used a slightly different geometry, where instead of counter-propagating beams, they were coming in at approximately at right angles, and by changing the magnitude of the coupling, we were able to smooth out that curve. So here's that same curve that you saw before that shows the vector potential as a function of the Raman detuning for this new geometry. But for the moment, this is a uniform real magnetic field. So let me just look at that curve again. This is a lovely curve. Basically, we learned how to do the experiment a little bit better between the last one and this one. You know, the noise went away. You know, the postdocs and the graduate students work a long time in the laboratory, and the noise goes away. It's the way it always works. With good students. But this is the detuning of the Raman field. But if I put on a gradient, that detuning can turn into the position along the y direction. And if the magnetic vector potential has this form, where this is the x, the y, and the z component of the vector potential, then this is the form of a vector potential in the Landau gauge for a magnetic field in the z direction. So that's what we want to create. So we do that, and there it is. These are the results. We turn on this gradient of the magnetic field, we release the Bose condensate, and when there's no gradient, then we get the usual picture. This is just a blow-up of the pictures you saw in the other slides. And then when we reach a certain threshold, we get these black spots. What are those black spots? Those are vortices. Those are rotating atoms that must have 0 at the center, because the phase of the wave function as I go around winds up by 2 pi. So at the center, it would be multi-valued, so it has to be 0 at the center. This represents, if this were an electrical system, it would represent 1 flux quantum. Here it represents 1 quantum of rotation. And as I increase the gradient, which is like increasing the magnetic field, I get more and more of those vortices appear in the condensate. So this is the the physical proof that the effect of putting on this Raman coupling with a spatial variation, that the effect of that is to produce an effective magnetic field. Now, I find this absolutely remarkable because remember, everything in this experiment is static. The laser beams are static, the magnetic field is static, it has a gradient, but in time it is static. And turning on that gradient, just increasing that gradient, makes the condensate rotate. It rotates in just the same way that it would rotate if you stuck a laser beam into it and stirred. And that is a good way of putting vortices into a condensate. And you can make this same kind of picture by putting a laser beam in and stirring it around. But nothing is stirring anything. It's just static magnetic fields making something that is the equivalent of a magnetic field if we think of these particles as being charged particles. Well, this is exactly what we wanted to do. Here is what happens if you wait a while for the I'm sorry. The next one is what happens if we. Well, okay. Let me explain what's going on here. What we're doing here is to turn on the gradient magnetic field and take pictures of the cloud after waiting for various lengths of time with all the fields on. The pictures are always taken with the fields off and after a time of flight. It's very important that that you understand that these are time of flight pictures, because in place, that is when the atoms are trapped, this vortex core is so small that we cannot see it. We do not have sufficient optical resolution to see the vortex core. It's smaller than the wavelength of the light. But once you allow it to expand, that vortex core becomes bigger, and then you can photograph it. And so all these pictures are taken after a time of flight. I forget, maybe 20 milliseconds of time of flight. And the times that are shown here are how long we allow it to stay in the trap before we release it. So this is a picture where we did not allow it to stay very long at all. There are no vortices here. Why not? Because the vortices have to come in from the outside. Just as happens in the case where you rotate the trap, when you rotate the trap, what happens is that vortices nucleate at the edges of the cloud, and then they come in. And we see exactly that happening here. After 150 milliseconds, we see that a number of vortices have appeared at the edge of the cloud. And after a longer time, those vortices have come into the cloud. And now, as you wait longer and longer times, you see that there are fewer and fewer vortices. Why? Because think of this as applying a uniform magnetic field to a conducting body. There's a certain amount of flux, and the conductors want to screen out that flux. And the bigger the area, the more flux there is, and the more flux quanta are needed in order to screen out the flux. Well, as time goes on, the number of atoms in this condensate decreases for sad reasons. But the number of atoms decreases. And as the number of atoms decreases, the area decreases, and the number of vortices needed to screen out the effective magnetic field also decreases. Now, why do the atoms decrease? Well, the Raman fields make the atoms scatter photons off resonance. We detune a lot from the upper state, but we can't detune an infinite amount. And so every once in a while, the atoms will absorb a photon, and when they do that, they get a lot of momentum, and they leave the condensate, and so that's what we're seeing over a time scale of some seconds. But on a time scale of milliseconds, we can see the vortices come in, and we can see the kind of behavior that we wanted to see. Well, okay, I have no idea how long I've been talking, but I see the clock says it's 11:30. And so you see what happened was I had my watch And then when it gave the alarm to tell me to take the medicine that I refused to take, then I had to touch a key, and the key stopped the stopwatch. So I have no idea how long I've been talking. But you're so enthralled by what I'm saying that you don't care how long I've been talking, right? Okay, so I think I'll go quickly through the rest of this, because the rest of the story that I want to tell you is really just an amusing story. We're probably not going to use it to do any interesting physics, but we could ask ourselves the question, have we really created a vector potential that has the properties that a real magnetic vector potential has? In other words, we've shown that we can physically create something that acts just like an artificial magnetic field. Can we also have a time derivative of that vector potential and make something that looks like an electric field? And of course the answer is yes, or I wouldn't be talking about it. Now maybe I would be talking about it because it would be kind of interesting if we could make a vector potential that gave the right answer for a magnetic field but gave the wrong answer for the electric field. But no, this one is just like a real vector potential. It gives the right answer for the magnetic field and for the electrical field. So here's the idea behind the experiment that we're going to do. You know that if you make a long solenoid and put current into it, that there is a magnetic field on the inside of the solenoid and no magnetic field on the outside of the solenoid, but there is a magnetic vector potential on the outside of the solenoid, and that magnetic vector potential has real physical effects. And you know it has real physical effects because you know that if you change the current in the solenoid, that a test charge here will feel an effective electric field and be accelerated. And in fact, if you look at this down from the top, you have this circulation of A, and if you change A, then you're going to get a circulation of E going around, and of course this is how a transformer works. You don't have any magnetic field in the secondary of the transformer, but nevertheless you have an A field, and that's one of the ways of thinking about how a transformer works. Of course, you can also think of it in terms of the flux that's in the secondary coil. You don't have to think about it in terms of the A field, but if you want to, you can think of a real physical effect from having a non-zero magnetic vector potential, even though the magnetic field B is zero. And what we're going to do is think about what kind of an impulse we can give to a test charge that is here if we change the current in this solenoid, which is changing the vector potential, by a certain amount. So the force on the charge is just the charge times the electric field, and the electric field is just the derivative of the vector potential. So if we ask what the impulse is, that is the integral of the force over time, which is the change in momentum, then we just do this calculation. You find that the change in momentum is the change in the vector potential, because remember, vector potential has units of momentum. It's not surprising that changing the vector potential by a certain amount will change the momentum by that amount. So that's what we're going to do. We're going to do an experiment that is the sort of spiritual equivalent of this transformer experiment. So what we're going to do is we're going to change the vector potential by changing the detuning. It's going to be a uniform vector potential, no magnetic field at all, just like in the case of the outside of a solenoid. No magnetic field. We're going to change in time the detuning, so the vector potential will follow this red curve, and we expect the electric field to then have a pulse, because it's equal to the derivative of this, it's proportional to the derivative of this, and the integral of this pulse will be the momentum. So what we're going to do is we're going to start at some value of the A field, and we're going to, in this experiment, at least in this first experiments that I'm going to show you, we're going to always make the final A field be its maximum value. We're going to go to a very big detuning so that the final vector potential is either plus or minus twice the photon momentum. These are the maximum values that it can have. Why do we do that? To make the whole analysis simpler, because remember, when we go to a very large detuning, the dress state becomes essentially one of the magnetic sublevels, either the plus or the minus one, and the other ones have almost no population. So that the analysis of what has happened to the atoms will be easier because they will all be in a single quantum state. Okay, and then we're just going to measure, we're going to turn off after having made this change, we turn off the Raman coupling. This is what I just told you, that the M state is nearly pure, and we'll just measure the momentum of the atoms. And it's going to be, and that measurement of the atoms, since all the atoms are in one state, will be a measurement of the mechanical momentum, and we'll see how much the mechanical momentum changed. So here's the picture you've seen before of what the vector potential looks like as a function of detuning. We're going to start at some place here, and we're going to change the detuning. So this is, say, a detuning at here. That means that the vector potential is here. We're going to change the vector potential to here by making the detuning very large, way out here someplace, and see what the final momentum is. And remember, the initial momentum was 0 because the atoms were trapped. They weren't going anywhere. And so we measure this, and there's only one spin state, and we measure what the momentum is. And then that gives us a point on a curve that we're going to draw of how much we changed the vector potential compared to how much we saw the momentum change. And let's see. So here's a picture of that. So this is how much the momentum changed. This is how much the vector potential changed. And you can see that it's just linear, and it has a slope of 1. In other words, it confirms that the impulse given to the atoms, the mechanical impulse given to the atoms, is equal to the change in the vector potential. Now, what did I skip over? We did another experiment where we left the atoms in the trap. So the usual experiment is that we turn the trap off and see what the momentum of the atoms is by seeing how far they go in a certain time of flight. But of course, we can also give the atoms a kick and leave the trap on. What will happen then? The atoms will oscillate back and forth. And by looking at the amplitude of the oscillation, we can tell what the amount of kick they got is. And by looking at the frequency of the oscillation, we can tell what their mass is. Remember I told you there was a different effective mass? Well, I haven't said anything about that. But now, because the atoms have a different effective mass, they will have a different oscillation frequency, because the oscillation frequency is given by the square root of the ratio of the spring constant to the mass. The spring constant stays the same, but the mass changes, and we find that indeed the oscillation frequency changes, and the size of the kick tells us how much momentum they got, and these points here were measurements based on those kinds of measurements, seeing how the atoms behave when left in the trap. And you can see they're completely consistent with the other measurements that were made based on their time of flight, how far they go during time of flight as a measurement of their momentum. So, more recently, things that I don't have time to tell you about, using this same kind of Raman coupling, Ian Spielman and his team have been able to induce the equivalent of spin-orbit coupling. Spin-orbit coupling in condensed matter physics is a coupling between the momentum of the electrons and their spins. And this becomes important for things like topological effects in semiconductors and topological insulators. And they've been able to induce this kind of spin-orbit coupling in this atomic gas using the same kind of Raman coupling, but just operating in a different regime of strength of coupling. Using Raman coupling, they've changed the nature of the collisions between the atoms so that these atoms that normally would only have S-wave collisions appear to have higher partial waves because of the asymmetries induced in the way in which the atoms interact because of the Raman coupling. And just very recently, they've seen the classical Hall effect, and this, of course, is a beginning of the push towards seeing the quantum Hall effect. So can we get to the quantum Hall effect? Well, in order to do that, we need to have a large enough field. And how large a field do we have to have? Well, in order to get to the quantum Hall regime, you need to have a field that is so big that the number of flux quanta that are induced into the system is about equal to the number of charge carriers, or in our case, the number of atoms. And we're not there yet. We don't have that big of a magnetic field, but what are we going to do to get it? Well, one of the things is we can increase the value of the vector potential. And one way of doing that, remember I told you we couldn't make a vector potential any bigger than twice the photon momentum, plus or minus? Well, that was because we only had 3 levels. If we have 5 levels, then we can transfer 2 more photon momenta to it, so we can double the amount of vector potential by going to f equals 2 instead of f equals 1. We can increase the gradient of the field, but of course, that means that we have to reduce the size of the sample because we want to be in the linear regime, or approximately in the linear regime over the size of the sample. So we have to decrease the sample size in that direction. But there's nothing that says we can't increase the sample size in the other direction to get more atoms so we have more signal to noise. And we want to reduce the number of atoms, so what we'll do is we'll divide the sample into pancakes, into slices, so that each individual slice only has a small number of atoms, and each one of them will behave like a quantum Hall system. So that's part of the idea of the direction in which we want to go to see this a quantum Hall effect with and really the fractional quantum Hall effect is the thing we want to do, because in condensed matter physics, certain fractional quantum Hall numbers should yield systems that have very strange properties, things that have non-abelian behavior in their interchange statistics. And that's one of the things we'd like to see in our neutral atom systems. It's been very difficult to see it in real systems. So these are the conclusions. We've been able, with Raman coupling, to simulate a magnetic vector potential, a vector gauge potential. By adding a curl, we've been able to simulate a magnetic field and produce vortices in a non-rotating system. I mean, this is really, and I want to emphasize how wonderful this is. Because if I rotate a sample, then there comes a certain rotation speed where it becomes energetically favorable for there to be vortices in the system. And if you keep rotating, those vortices will stay there because they're energetically stable. In our case, there's a certain effective magnetic field where it's energetically favorable to have vortices in the system, and if you keep that magnetic field on, those vortices will stay there. If you were to stop rotating, those vortices wouldn't be stable anymore, and they would find their way out of the system because they would have a lower energy to be out of the system. So those vortices are not stable unless you keep rotating. Our vortices are stable even though we're not rotating it. They're stable as long as we keep that synthetic magnetic field on. So I just find that remarkable. It rotates without rotating. And this sort of trivial effect that we were able to show that it's a complete effect of this magnetic vector potential produces an electric field. And we've been able to do some interesting things, and stay tuned for more information about that. This spin-orbit coupling has been published, and soon there should be publications on the collisions and on the classical quantum Hall effect, and we're hoping that we can move toward the quantum Hall effect as well. Thank you very much.
Thank you, Professor Phillips.
Hi. For the quantum Hall effect, I would say that the condition to get it would be to have the magnetic length much smaller or smaller than the sample size. That's equivalent to say that.
Yeah, that's essentially the same thing. Okay. That's right. So I just said it in different words. You're absolutely right. Having the magnetic length be, it amounts to the same thing. That's absolutely correct.
When you look, going back to the spin-orbit interaction, if you look at things like the Zitterbewegung, you can calculate this kind of thing, the trembling motion, for the same kind of system. Actually, we've done this a couple years ago. And the thing is, how can we, in principle, measure this in this kind of system? Because apparently you have the Bose-Einstein condensate there, sitting there, right? how much of a single particle? It's a bit.
Yeah. Okay. So that's a good point. So everything that I've shown you so far, except for the nature of the vortices themselves, has been a single particle effect. The vortices, of course, won't have a core unless there are interactions between the particles. The fact that the core size is small comes from the fact that the particles interact with each other, and that can be understood completely on a mean field basis, and the size of the core in situ is going to be approximately the healing length of the condensate, what in a superconductor would be called the coherence length. In the Bose condensate, we call it a healing length. And that is something where you have to take into account the interaction between the particles. But generally, this has been a single particle treatment. Now, looking at, of course, in the fractional quantum Hall effect, we're really looking very much for interaction effects. And there are a number of things that are going to have to be done in order to get those effects to produce the interesting physics that we want. Besides just getting the magnetic field up, we're going to have to play with the interactions as well. So there's a lot more work to be done. So now, as far as for the spin orbit, the spin orbit that has been demonstrated so far is a kind of a funny spin orbit interaction. It's a particular mixture of what's called Rashba and Dresselhaus spin orbit coupling that are just enough of each that they do absolutely nothing. And there is an effect because of the Raman coupling, and that effect would be what would happen if you had these equal amounts of Rashba and Dresselhaus coupling and also had a magnetic field on. Then there would be an effect due to the spin orbit, but in the absence of that magnetic field, there would be no effect at all. It's just a different bookkeeping that you would do for the Hamiltonian of the atom to make it look like there's a spin orbit coupling when in fact it does nothing. So in fact, it's not the most interesting thing in the world. But there are some ideas to try to make it be a more interesting kind of spin orbit coupling that involve using more Raman lasers coming in from different directions. So we're really just at the beginning. We're just starting to crawl on this spin orbit business.
Bill, I wanted to ask a question about the vortices and the conservation of angular momentum. So, I mean, you demonstrated very nicely that in the case of linear momentum, when you multiply the population and the individual components, that it sums to zero for the linear momentum.
Yeah.
In the case of the vortices, how does that?
Yeah. So where does the angular momentum come from?
Yeah.
Well, so that's a good question, and I'm not sure that I've got a particularly good answer to it. Obviously, the application of a magnetic field to an electrically charged system will create angular momentum of the charged particles. But if we count all of the angular momentum, that is the canonical angular momentum, that's going to be conserved. Now, one of the things that I haven't really spent a lot of time here doing, because I have to admit that I find it a little bit confusing myself. You see, I was never that good in theoretical physics. That's why I became an experimentalist. But one of the things that has always confused me about electromagnetism is the concept of canonical momentum as opposed to momentum. Now let's look at this picture here. So over here, this obviously is just the momentum. I mean, we don't have to talk about what kind of momentum it is. Over here, this thing that I've called P is not the mechanical momentum. It's the canonical momentum. It's the momentum that is canonically conjugate to position in the Hamiltonian. This quantity that's inside the parenthesis, that's the mechanical momentum. Now, when I apply a magnetic field, then I have to think about the same kind of thing for angular momentum, that is both canonical and mechanical. Or another way of thinking about it is that if I want to ask about what happens to the phase, the wave function, as I go around a loop, I'm going to have to include a term that has to do with this magnetic vector potential. And so I think that the proper answer to your question has to do with a correct accounting of that kind of thing. Now, that's not a very satisfying answer. At least it's not very satisfying to me. The kind of question that I would want to ask if I were sitting there and you were sitting here and you were standing here is, what pushes these atoms around? What is it that's making these atoms turn? Because after all, you've got this system that seems to be very symmetric. What is it that can make this thing turn? What breaks the symmetry of the Hamiltonian? Well, if you look at the Hamiltonian, you can see that there is an asymmetry about the way in which you've coupled together the different Raman states that have the coupling goes in a particular way from higher to lower angular momentum. So there is a breaking of the symmetry. The fact of the matter is I'm not entirely satisfied. I'm not quite happy yet with the kind of answer that I'd like to be able to give to your question. So we need... So the gradient of the B field is certainly absolutely essential for, and of course, as you know, a magnetic field itself breaks rotational symmetry because it has a screw nature to it. And the gradient is absolutely essential for getting the different components of the Lorentz force, because the Lorentz force acts always perpendicular to the velocity, regardless of where the velocity is going. It looks like you can only have force along the laser beams, but that's not. But of course it has forces perpendicular to the laser beam, and that's where that comes from, is from the gradient of the B field acting on the magnetic moment of the atoms. So it's a kind of a subtle thing. In the one direction, you've got the momentum transfer from the laser beams. In the other direction, you've got the gradient of the B field acting on the magnetic moment of the atoms. Two completely different physical origins that produce something that looks exactly like the Lorentz force. I think that's amazing. I really still don't understand it, how it all works together. I mean, I can write it down, but it's just remarkable that it works out this way. And I'm not yet fully satisfied. And as Alain will tell you, I'm not easily satisfied.
I had another question, but before going to the other question, I would like to complete this question, or after your discussion, in the following way. At the end of the day, is it really matter which is rotating, or is it just the gradient of the phase of the wave function?
Well, now that's a loaded question, if I ever heard one. To me, the gradient of the phase of the wave function in quantum mechanics is physical motion.
You think so? Okay, every time. In all cases.
No.
Usually I agree with you, but here...
No, not every time. Not every time. Because when you have other fields, then it's not such a simple answer. Okay. But in this case, it is physical rotation, because if it weren't, when we turn everything off, we wouldn't see that pattern. That pattern that we see of the expanding vortex core, that's done in the absence of any of the couplings. So that shows that it's rotating. It can't produce that expanding whole unless it was rotating. So it really is rotating.
Okay, so my question is another one I hope you are going to appreciate. In this equation of a solenoid, and out of the solenoid, the magnetic field is zero, but the vector potential is non-zero, and of course this gives rise to the famous Aharonov-Bohm phenomena, etc. In your
and of
case,
course, Bohm, as we know, had a very long and wonderful relationship with Brazil.
Yes, and not so much with United States, as you know,
not
because
so much with the United States.
he was black.
Well, that's true. I mean, we've never been so happy about people who dissented politically in certain directions in the United States. And but I understand that he was very fond of feijoada. But
don't try to avoid the question.
I'm trying to avoid, which I know is going to be a very hard question.
The question is, do you have any kind of possibility in your system to mimic that situation? That is a situation where apparently the atom is submitted to nothing except for a fictitious, between quote, vector
so that's
potential.
a good question. And so we have not yet figured out how we might do that, because of course the great thing about the Aharonov-Bohm effect is that you have this region that is that has the magnetic field, and then you have the region outside of it that doesn't, and you go around it. And the trouble is we don't have that geometry. We just have, you see, our geometry is more. You see, I should realize that using that electrical analogy is a little dangerous, because really we restrict ourselves to a region way out here where the vector potential is uniform, and in order to do Aharonov-Bohm, you have to go around here, and we don't see any. We haven't figured out a way of doing it. Now that, yeah. So if you have a clever idea, we're all ears.
I have one question. I don't know if I understood it right, but if I admit that the atoms, under the point of view of translational motion, may be considered as classical, the atoms itself, as far as the spatial motion of these atoms are concerned, I suppose they're considered classical.
For certain things, I would say that for the case of the vortices, not so much, because there I use the irrotational property of the fluid to understand why I get the vortices. And that means that I have to think of the atoms as having a wave function. But for most of the things, I would say you're right. We're treating the atoms classically. No. Well, okay, let's get to the question. We'll see
the
whether...
question, therefore,
whether,
admitting that each atom...
Because these families, of course, were where I use that word because of its origin in velocity selective coherent population trapping, which Alain did many years ago.
Well, anyway, admitting
yeah.
that the motion of each atom is classical, then you would assume that the only relevant fields are E and B. The particles won't see A. There is no Born-Aharonov effect.
That's true, but I don't think that's the only effect that an A field has. You see, I mean, and furthermore,
That's the point I get confused.
Right. So I think that I've also been thinking about Alain's objection. So I think I agree with him because of the fact that you can't have a superposition of different momentum states with classical. But I don't think that has anything to do with your question. Your question is more fundamental and is really a question of whether a non-quantum mechanical system will respond to an A field.
Yes, that's my point.
I guess my feeling about that is it's a matter of taste. That is, in real electromagnetism, I could choose to do everything without ever thinking about the A field. And sometimes that would result in a great deal of complication because it's so easy to do things in terms of the potentials. But I'm sure I could always find a way of explaining what happened without using the vector potential. I would invoke Lenz's law for flux or something like that. So I'm pretty sure that whether or not the particles are thought of as being quantum mechanical doesn't really matter for things like the momentum transfer, just as it doesn't matter for a transformer. You don't have to think about a transformer quantum mechanically. A transformer works, and I can tell you that it works because there's a non-zero A field, and the rate of change of that A field induces an EMF around the secondary. But you can say, no, I don't want to think about A fields. I will think instead about flux.
No. Flux is black magic. It's very convenient to do the calculation of a transformer, but it's a black magic. You don't see where the force acts on the particles.
All theoretical physics is black magic. It's just a matter of which color of black you choose to use.
But yes, that's my second question. You have E given by minus dA dt.
Right.
So if I add E to plus the dA dt equal to 0, I have to guarantee that the rotation of this sum, this field that results from the sum, and plus the divergence of that field is 0.
Yeah.
How this is guaranteed?
Well, okay, I guess I don't know the explicit answer to that. I believe that it is because it has the right form. That is, considering the fact that we know that it has to be gauge invariant, the fact that I can write the thing correctly in one gauge means I should be able to write it in any gauge. So I'm pretty sure that as long as I deal with things that don't depend upon the dynamical aspects of the field. For example, there's not going to be any radiation from here. So this is not going to give me Maxwell's equations, okay? So as long as I restrict myself to a certain class of electromagnetic phenomena, which I think will fall into the category that you're telling me about, I think it will work. But how it does it in detail, I haven't thought about it. But, I mean, it's an interesting question. Maybe we should look at that more carefully to see if there are interesting deviations from true electromagnetism.
Because I'm referring to this last drawing you made. There is only, the B field is concentrated inside the solenoid.
Right.
No matter if you vary things.
Yeah.
Many people try to get around the Raman effect by saying that it's impossible to vary the field inside the solenoid without having something happening outside.
People say that, but that's, I think that falls into the category of what in technical terms is called bullshit.
You should be fair. The beauty of Raman is that you don't need to change anything.
Right.
The beauty of Aharonov-Bohm is that you don't need to change the magnetic field in the solenoid.
I agree.
And this is why there is no discussion about it.
Yeah.
Because as soon as you impose a change in the solenoid, it's not clear what it means to have an infinite solenoid. How can you change a current inside something which is infinite? Where are your sources? Where is your knob, etc.? So the beauty of Aharonov-Bohm is that you don't change anything.
Right, and I think the other beauty of Aharonov-Bohm is that there's no other kind of magic that you can apply to explain why it happens. You are forced, I think, to think about the vector potential. But, you know, we say a vector potential isn't real, that only E and B are real. What is real? You know, I mean, do we ever actually measure E and B? We measure the effects of E and B on test charges, right? So I'm not sure that even that is, you know, remember I told you I'm not a very good theoretical physicist. I'm interested in what I can see in the laboratory. And if somebody tells me that I change something and something else moves, then there's something real going on there. And no, of course, no. This was no. We certainly don't have. We certainly don't have a well. Our experiment doesn't really have real cylindrical symmetry, but all of the interesting things do happen in a plane and perpendicular to that plane. So I don't think that the failure of cylindrical symmetry is important, except for explaining things which I'm glad nobody asked me about, as to why those clouds are extended. You know, there's little details there that have to do with.
You suggested other magic way of explaining things. So, do you have a way which is not so magic? I mean, rather than going to potential vector, etc., 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 can you make a detailed analysis of, well, my laser beam is here, I play with that, etc.? I mean, is there another picture for understanding the kind of effects you are seeing?
Okay, so I believe that there is, but I haven't carried it out. In other words, what I've done is I've sort of thought about it for a little bit and satisfied myself that if I did take the time to do it, that I could probably figure out how the momentum is transferred, but I haven't done it. Okay? Now, on the other hand, Ian Spielman's done a complete treatment where he's done this whole thing using Berry's phase. But I think that's the opposite direction from the way you want to go. So if you do the whole thing using Berry's phase, then it all works out just as well. You can see that there's a Berry's phase for going around a loop, and that has the same effect as a magnetic field. So if that's satisfying, well, what does that mean? Let's say that something is really quantum.
Berry phase will be associated to a wave function. You cannot think of the atom as being opposed.
Okay, so a lot of people would say that in order to be really quantum, there has to be an H-bar here someplace. So there's no H-bar, but I agree. I don't think that should be the only. You know, your point was that you don't, and I think I'm with you on this one, except for the vortices. Well, for the Berry phase, yes. Okay, for the Berry, but that just means that if you choose to do it with Berry phase, you're forced to do it quantum mechanically. I'll agree with that.
You can do Berry phase for classical optical waves, but it's a wave.
Sure. Yeah, so I will agree with that until I think about it more.
No, okay, I think. Pushing forward this analogy, I mean, can you, for instance, the shift in the momentum, you interpret it as a vector potential, but can you split that shift in electric charge and potential itself? Can you make...
Can I? Yeah, and the answer is,
is there an analogy to electric charge here?
Yeah.
I mean.
Well, as far as I know, I can never disentangle maybe I shouldn't use the word disentangle in front of Alain Aspect, but I can never separate the charge and the vector potential. I only think about the product. I can never think about anything other than the product of the charge and the vector potential until I finally integrate the force to get an impulse, and then the impulse is the never mind. That was wrong. The impulse is the product of the vector potential and the charge. So I can't separate them. So in a certain sense, one of our public relations people suggested that when we did the first experiment, that when we made just a vector potential, that we should claim, well, we hadn't made a synthetic magnetic field, but we'd given the atoms a synthetic charge. And then when we put a gradient on, then we'd had a synthetic magnetic field. It was a nice public relations idea, but I don't think it has any physics to it.
Thank Professor Phillips again.